Good afternoon. Welcome to the Forest Climate Working Group Learning Exchange Series. My name is Lauren Cooper, and I'm the lead of the Forest Carbon and Climate Program at Michigan State University, and we're so pleased to host the 2018-2019 Exchange Series. The Forest Climate Working Group is a diverse group of forest interests, including landowners, industry actors, conservationists, academia, and those active with carbon markets. The group has worked together for 10 years to advocate for state and federal policies that work to ensure sustainable forest use and prevention of land use change and forest loss. We have currently been in the process of reinvigorating our focus and activities, and we welcome inquiries into our work. So please reach out if you have any questions or you think your organization may be interested in joining. We do have the full lineup, which you can see here up on our website, including individual registration links. So please head over there if you'd like to register for upcoming events. You will receive calendar invites. So if something jumps out, go ahead and get signed up now and you'll get reminders. Also take a moment to highlight our next session, which will be March 6th, and we'll feature two folks from the Nature Conservancy, Campbell Moore and Beth Wheatley, and they'll present on their current work, Climate Action in Coal Country, engaging landowners there. And again, you can register for this session today at our website or by clicking a registration link in our email if you're on our email list. So to get to today's speakers, we're really pleased to introduce Elaine Oneil, who's the Director of Science and Sustainability at CORRIM, which is the Consortium for Research on Renewable Industry Materials, and Dr. George Berghorn, Assistant Professor of Construction Management at Michigan State University, who will present, together they'll present an overarching, under the overarching topic, Getting Forest Management and Land Use Carbon Accounting Right for Harvested Wood Products. We're really excited to let Elaine and George get started, but before we do, I'd like to share a few details, particularly if this is your first time joining one of our webinars here. To automatically receive registration details and information regarding upcoming webinars, please email forestc@msu.edu and you can join our email list. Attendees today are qualified to receive 1 CFE credit through SAF. So for those interested in this credit, you can reach out to us at forestc@msu.edu, but we do automatically send that information along to SAF. So if you have any questions, reach out. This session is being recorded and will be posted on the web along with any supplemental materials such as presentation slides or links in the next week or so. If you've registered, you'll receive a follow-up email and that will let you know when and where to find it. But again, it's at our website. And we'll have a link at the end of the presentation visible on the screen. This session will be followed by a Q&A, and we're going to let both of the speakers go all the way through and we'll collect questions. So we do encourage you to send in any questions through the chat function whenever they cross your mind. Feel free to submit them, but we won't, we'll do a Q&A with both speakers at the end. So to submit a question, there's a chat button on your Zoom interface. It's a little drop-down triangle next to it. And here you can offer up questions again at any point, and we'll compile them and present the questions to the speakers in the Q&A session. If you're calling in on the phone, but you can email, you can also send any questions directly to us at forestc@msu.edu. And in the case of outstanding questions, we will work with the speakers and have these addressed and put them into a Word document and save as a PDF, and we'll upload that with our presentation material. So if we don't get to your question, apologize for the limited timing, but we will certainly present it to our speakers and get a response. And so with that, that's enough for an introduction. Elaine, will you please share your screen and begin your presentation?
Absolutely. Let's hope the technology works. Okay. Can you folks see that screen? Okay, from beginning. Now, just hang on one second. There, you should be able to see the first page. Is that correct?
Looks perfect.
Okay. Thanks, Lauren, for that introduction. And I'm going to, because I'm on a time limit here, I'm going to leave that to stand and move directly into the conversation about forest carbon considerations, looking predominantly at the land use forum, and that's where my area of expertise is. So I'm going to start this conversation with a look at private forest timberland. and look at what it takes to grow it and keep it as a forest. Now, I find hardly anyone who doesn't like the forest when it's at this stage. We all love our trees. And now we love that they're also actively sequestering carbon at this point in time, and maybe less so in the winter picture than the summer one because it's cold outside, which most everyone in the country can agree. That was me, by the way. Now, except for the landowner, hardly anyone loves the harvest stage, which takes place once every 25 to 50 years over a 2 to 3 week period. I think we tend to forget that what ensures that all those trees in the background can continue to grow and hence sequester carbon is the opportunity for profit and reinvestment. And the investment is not inconsequential, from sowing those seedlings, doing the site prep and the planting and the protection, to managing that forest for 25 to 50 years is not an inconsequential investment. There's a tremendous amount of money, time, and labor involved in regenerating forests and protecting them from all sorts of hazards. And calling out the example of small forest landowners, the Townsends, putting elk browse protectors on every one of their seedlings and rechecking and replacing them every year until that stand is above browse height. They don't like this, but I like to call it the diaper phase. It seems to fit because it's a labor of love with high uncertainty regarding returns. Then there's a long wait, sometimes until the next generation inherits their land. Barring a whole host of potential natural disasters, that kind of investment will generally lead to a well-stocked forest stand that can sequester a substantial amount of carbon while it is growing to maturity for the next harvest. That kind of growth you can see here in a carbon in tons per hectare. This actually just looks at the forest component, not the soils and the understory and all the rest of that. But once you plant that forest, you're starting to sequester carbon, and then at age 50, in this example for the Pacific Northwest, you're harvesting, and then you're planting a new crop again. That little blip at year 25 is when you're doing some kind of a commercial thin to improve the quality of the stand. Take a look there. So this is 0 to 100 years on the X, and the carbon in tons per hectare is 0 to 180 on the Y axis. So at about 100, or at about 50 years, there are about 160 tons per hectare of carbon sequestered in the trees in that particular individual stand. Now I want to contrast the forest where investment was substantial, continuous, and successful, that's the one on the left, with the one that was left for nature to take its course, that's the one on the right. These are in the same climate here in the Pacific Northwest, but the one on the left is producing in the neighborhood of 60,000 board feet of saw timber, and then one on the right will be lucky to produce the equivalent of maybe 16,000 board feet of saw timber, or maybe mostly pulp. The second alternative does not make good use of the site, so from a resource use efficiency standpoint, it's not necessarily a good alternative, but it is the alternative when there really isn't that opportunity for investment and recovery of investment through harvest. Now, because tree volume is directly correlated to carbon sequestration, the acre that you don't manage doesn't sequester as much carbon either, and it doesn't do it as quickly. And that's shown by the comparison here of the Pacific Northwest no management natural regeneration alternative, in that you should be able to see it as a dotted purple line. There's a substantial difference in the ability for forests to sequester carbon under management versus no management. In fact, even if the forest is never harvested, failing to invest has significant long-term consequences on the amount of potential carbon that can be sequestered per acre, and as noted on the 3 solid lines on the chart here. The black line at the top, now I don't know if you guys will be able to see this, my cursor is following that black line, that's the managed forest, the no harvest alternative, and that particular one would be more akin to that picture of the large Douglas fir. An unmanaged forest, if you do nothing, you might will get regeneration here in the Pacific Northwest, not in all regions, but in the Pacific Northwest you can get regeneration, but it won't necessarily be as, it'll take quite a bit longer, and it won't necessarily be as productive. And then I would say that that alder stand is more like this bottom gold line because it's not a fully stocked forest. Now, these lines represent the average of a number of different references that we've looked at to look at these comparisons. The first two were modeled within the work that we do. Now, in terms of management and investment, how big can that difference be? This one, we're changing regions. We're going to the southeast, US Southeast pine plantations. And on that bottom, I found this particularly stunning. In 1940, the annualized yield measured in dry tons per hectare per year on the y-axis was about 1 dry ton per hectare per year. That was just a natural stand. With planting and then the advent of site preparation and fertilization and weed control and tree improvement, and now they're in that clonal biotech area, you're looking at 13 times more yield, which means 13 times more carbon sequestration. And then at the same period of time, you have the rotation age dropping dramatically from 50 years to about 18 years. That's that black line flowing down from the left to the right. Clearly, with investment, we can grow trees bigger, faster, and better, but that investment does come with the expectation of harvest. Now, this is also in the southeast, and now that we have 2017 RPA data, we'll probably update this one. With that increase in investment, what we've found is that not only is there an increase in efficiency per acre, but also an increase in acres in production. There was a slight drop from the 1950s to the 70s, and then the acres in production in the southeast has actually been increasing, despite the fact that we're harvesting a tremendous amount of fiber, and that's shown in that black line, that continuous harvest of fiber. So what we're seeing is that the land is sustaining its carbon, the carbon volume on the land, while we're continuously removing carbon and putting in for other uses, whether long-lived products or pulp, or currently pulp pellets. Now, I want to go back to that clear cut for a minute, and I want you to look beyond it to the forest land behind it. That particular forest land is all owned by the same landowner that's doing the harvest. There is a myth of the carbon debt that arises because in this harvest scenario, because we only look at the clear cut and forget that the land behind it is part of the package deal. The carbon on a single acre, like that clear cut, looks like that big swing in forest carbon that we're showing on this particular chart. Here we have 200 years on the x-axis through time, 50, 100, 150, 200, and then metric tons of carbon per hectare. I mean, this is stylized, but it's there to demonstrate the point that in a single acre, yes, you get this increase and decrease fairly dramatically, 50 to 150 metric tons of carbon per hectare on a single stand. But when you start at a small landscape, it starts to look more like that small squiggly teal line. And then at scales that provide long-term sustainable wood supply, it looks like that black line. In other words, it's nearly flat. So that example where I talked about the Townsends, they have about, I want to say 300 acres. And they have a long-term management plan. They know exactly what they're going to do and when they're going to do it. They probably look like the little squiggle, but they don't supply they're not the only supply to a mill. And when you want to maintain a milling infrastructure, you basically need that flat line of supply, which means you don't have a carbon debt. If you're not managing sustainably, then you tend to lose your markets because there's no way for those mills to continue to operate without a stable supply. When supply dries up, as it has in the western U.S. where the forests are predominantly federal lands, the infrastructure disappears and the opportunity to invest on remaining lands goes with it. And that's been a real unfortunate consequence in the past just about 2.5 decades. which leads to a very brief discussion on the difference between old forests and young forests in terms of carbon sequestration. These are a couple of my favorite pictures. I love both of those forests, but they have different consequences when we're talking about forest carbon and how we want to use forest carbon as a mitigation for climate impacts. Now, on predominantly old national forests, so this is data that includes the 2017 RPA data, what we're seeing is that your mortality, which is that red bar, is basically double the size of the net growth, which means that the mortality plus the net growth would be the total growth. We're losing 2/3 of our growth to mortality in our national forests. And I'd have to say, this didn't used to be the case, obviously, but this is a reflection of the age of the trees and the challenges that come with having old forests, a whole lot more wildfire and a whole lot more insects and disease on the land base. In terms of resource use efficiency, if that was the only thing we were measuring, and I'm not saying it is for national forests, they have lots of other purposes for being, but in terms of resource use efficiency, we could say this is not an efficient mechanism for maximizing carbon sequestration from the atmosphere. If we look at the Pacific Northwest as an example, here what I've done is I've zoomed into the Pacific Northwest region, which is Washington and Oregon. We clearly do have more carbon stored on public lands than private. We have an enormous number of federal lands and state lands in those two states. The public land, the growing stock, which is measured in million board feet, so this is basically billions of board feet, from 1953 up to 2017, so those are the 10-year RPA periods, is about, averages about 13.2, or about 13,000 board feet per acre on 25 million acres. By comparison, on private lands, you have about 16 million acres of timberland with an average of 8.8, or so 8,800 board feet per acre. That's about a 4,400 board feet per acre difference, or about 9 years worth of growth, given the average growth on stands in the Pacific Northwest. I'm calling out this particular point in about 1993, the spotted owl listing occurred in the Pacific Northwest, and we had a fairly substantial change to the way that public lands were managed, and that basically drastically reduced the acres that were harvested. So you did see an increase from that point in time of standing inventory, which has started to decline in this last decade, I think largely due to that mortality factor. If you want to look at total sequestration, the total amount that was taken out of the atmosphere, you have to look at what's left on the landscape, those two lines I just showed you, and then what was taken off the landscape in terms of harvest. In this particular case, I was able to go back to harvest records going back to 1965, so the 10 years, these are 10-year aggregates of harvest volume. And it turns out that when you add in harvest, the amount that is removed from harvest, the amount on each acre is now for public lands is 13.8, so 13,800 board feet per acre, and about nearly 12,000 board feet per acre, or about a little under 2,000 board feet per acre difference. So this is the difference is about 4 years worth of average growth on the private forest lands. So in the 25 years since we've largely ceased harvesting on public lands, the private forests have ramped up their productivity a lot, whereas the public forests have shown a slow decline in overall carbon removals from the atmosphere because of that mortality. Just a point to put this in a global perspective, a national perspective, and a global perspective. The tremendous resource use efficiency on private lands in the Pacific Northwest shows up in the national carbon accounts as a significant source of fiber. Those two states account for about 8% of U.S. forest land. That produces about 34% of the U.S. lumber and about 32% of the U.S. plywood. Now, 8% of the forest land, but recall that only about half of it is actually private, the rest is public. So we're getting a tremendous resource coming off of these lands that supports, that also still stores carbon, but supports an overall infrastructure. And that I always come back to the question, if we don't get it where else can we get that kind of productivity in the world? And the answer is probably nowhere. There's places where it grows faster, but not at the quality that we have here. I don't think I can stress enough that the markets that drive investment in forestry are what keeps forests instead of being converted to non-forest uses. We see that most dramatically in the Southeast, but also in the Pacific Northwest in regions that have very strong markets. Globally, you'll see places that don't have strong markets have more forest conversion to other uses. Now, I want to just shift gears a little bit from the forest to some of the other work that we've done in CORRIM over the past 20 years, and talk a little bit about this idea of tackle climate change, use wood. This is a copy of I'm going to call it kind of a coffee table layperson's book that was put out by, I think, Woodworks and the Canadian Wood Council. And it's a book that describes how the forest to the wood products LCAs support the idea that wood is part of a climate change solution. CORRIM has spent over 2 decades looking at the way wood fiber is currently allocated among products and where it generates the biggest bang for the buck in terms of carbon footprint, resource use efficiency, and optimal substitution opportunities that not only have a demonstrably lower carbon footprint, but which outperform alternative systems. So this particular chart looks at all of those comparative alternatives. We've tracked everything from the time we put the seedling, germinate the seedling, and we put it in the ground and we grow it and we harvest it and we take it to the mill and we divvy it up into all these products, and then we start looking at alternatives. A lot of that work has been done, so we have a pretty good idea of where the pluses and minuses are. Using this attributional LCA framework that builds on this primary data from literally hundreds of manufacturing surveys has given us this real clear idea of where the various products fall out in terms of efficiency. Here we're measuring efficiency in terms of fiber used per unit of product. So on the y-axis, we have kilograms of fiber needed per cubic meter of product, and we have lumber, I-joist, cross-laminated timber, which is CLT, plywood, particle board, and laminated veneer lumber, which some people call LVL. So you see this gradient of we need more wood fiber per cubic meter in LVL than we do in lumber, and largely this is driven by the density of the final product. Now, I'd say those comparisons are somewhat useful for us academics, and they meet the requirements for LCA because you have to put it on some kind of a unit, but they're not as useful as it is to compare resource use efficiency on what we're calling a functional unit. In this case, for a functional unit, we're using is a square meter of wall assembly. A square meter of wall serves a function just like a square meter of floor. Now, if you were noticing in that last chart, there's a bit of jostling around in terms of resource use efficiency per functional unit. And frankly, you'll see you got kilograms of wood fiber per square meter of wall. If you use a steel stud plus plywood, you're going to get the wood fiber used per square meter as the plywood. If you have the wood stud plus the plywood, you have more fiber used. And then if you have the CLT, you have this enormous amount of fiber used. So we've come to the conclusion CLT is not a very efficient way to build a wall if you're considering wood fiber used as a resource use efficiency metric. But on the flip side, because it's not very efficient from a resource use efficiency standpoint, it does store a tremendous amount of carbon relative to other alternatives. Here it's compared lumber to steel to concrete block to CLT, again, carbon stored in that wall. So if part of your goal as a builder is to have a building that has that serves as a large carbon sink, then something like cross-laminated timber or other mass timber products have some significant pluses over conventional construction. And finally, I want to say where mass timber really shines in terms of carbon footprint is when it can replace something like a reinforced concrete wall. Because on a net basis, it stores carbon emissions rather than releasing them. And that's shown in this particular chart, where 0 would be a net zero building where you either are emitting or storing any carbon dioxide in that square meter of wall. So everything to the negative side is actually storing more carbon dioxide than emitted in the production of it, and everything to the right is emitting more carbon dioxide than is stored in the final product. This is just one example of a comparative analysis. It builds step by step from the point of the seedling until the wood product enters the building as part of a wall. I would say that many more of these kinds of comparative analysis are needed, not just on the functional unit basis, but on the whole building basis, so that we can find the highest leverage for what is essentially a scarce natural resource, sustainably produced wood. And with that, I wanted to pass this on to George, because I think he has the other part of this story that I'm very much looking forward to hearing.
Great. Thank you so much, Elaine. This was a really great background, great introduction, and I know these presentations are coordinated, so I'll just take a quick moment to remind everyone that we will save questions to the end for Elaine. We do have a couple of questions and comments have been rolling in. Please feel free to continue to do so as George continues, and we'll have a nice Q&A when George is finished. So thank you so much, Elaine, again. And George, when you're ready, could you please share your screen?
Yep, I just need to, oh, there we go, sorry. I thought I had to get it, I thought I had to get screen sharing given to me. I apologize.
Looks great.
Okay. Good afternoon. Well, thank you, Elaine, for making that bridge so well between your presentation and mine. I'm going to spend a little bit of time this afternoon talking more about what happens once we bring this mass timber material, what be it glulam or CLT or nail laminated timber, into the construction process and start to explore some work that we're just starting to get onto the edge of at MSU that's starting to ask that question. How does the construction process itself contribute to the overall carbon budget of a project that's utilizing mass timber as the basis of the products for construction? And it's not in the slideshow, but I think it's important to mention that just last March, I guess 2 months ago, the end of December, the International Code Council has been going through their voting and vetting process for proposals for the new 2021 International Building Code, the model code that most municipalities in the United States use to create their commercial building codes locally. And there were 14 proposals that were put into the first group of proposals that were considered, that all dealt with expanding the use of mass timber construction in the IBC. All 14 of those proposals were passed by the consensus body at the end of December, and will be getting certified for final vote and inclusion in the 2021 International Building Code. And I mention that because really what we're talking about, and Elaine said it very well in terms of material substitution, is what we expect to see as municipalities begin to adopt this new version of the code. And we don't expect that to happen right away. There is some lag in the code adoption cycle among municipalities in this country. But as that new building code is adopted, what we expect to see, frankly, is substitution of mass timber for reinforced concrete and steel, which of course are the main constituents that we use in the structural and to some degree even the non-structural components of our commercial buildings in the United States. So with that being said, just in case anybody is not heard much about mass timber, I just want to give a very quick overview of some of what we're talking about here. Some very common products, mass timber products that are used in this construction type are cross-laminated timber and glue-laminated timber. CLT, cross-laminated timber, is constructed very much like plywood, where you've got alternating layers of wood and resin, and those alternating layers of wood are placed at 90 degrees to one another so that the grain structure, instead of running parallel in successive layers, is always running perpendicular. The difference with CLT is we're now making those layers, of course, out of dimensional lumber. So as you can see in the picture on the left, you end up with a very significantly sized panel. Those panels are both thick in terms of the number of layers that have gone into their manufacture, and they can be quite wide and quite long. Width is typically restricted by over-the-road transportation requirements, so 8 to 10 foot wide panels are most common, and then lengths are really just a function of what the manufacturing facility is able to produce on their presses. So panel lengths, can be anywhere 80, 90, 100 feet long. Glue laminated timber, on the other hand, lays successive lambs in parallel with one another, and again uses resin to bond those layers together. And you may get a glue lam panel, as you see in the picture in the upper right, or you may get a glue lam beam or column, as you see in the picture in the lower right. So the upshot of these materials is that we can make envelope components, so building walls, floor decks or roof decks, as well as the structural frame, out of these mass timber elements. Of course, the idea is if you're using CLT or glue laminated panels as your exterior walls, you're also reducing the size that's required in your structural frame, because those panels themselves are structural. So a large, robust structural frame is often not required in the same way as when we do reinforced concrete and steel. Just to give you a couple of examples of buildings that have been constructed using this, this modality. The first picture here is the T3 building in Minneapolis, 7-story commercial building that from the outside you would not know that this is a mass timber structure, but indeed it is. This was built within the last 2 years and is emblematic of the fact that there are designers and contractors in the United States that are moving forward with pursuing putting up mass timber structures, even without a current code structure that supports the easy adoption of this technique. So the current building code allows for up to 4 stories of mass timber, and when you see larger structures like this, 6, 7, 8 stories, they're either built on a concrete podium, so some of the floors are concrete, or they've had to get special permission from the local building office to put in heights greater than 4 stories. The building to the right is Brock Commons. Brock Commons is a dormitory building at the University of British Columbia. It's 18 stories, and it's, again, a mass timber, a CLT structure, and you can see floor slabs that are being lifted into place. And you can get a sense in that photo, if you've not seen it before, again, for what the size of these panels are like. And so it's possible with CLT. The final picture that I'll show, just to orient you with a project, and we'll talk a little more about this project in Brock Commons. This project is Candlewood Suites. It's a hotel, national hotel chain here in the US. This is a hotel building that was built on the site of Redstone Arsenal, which is an Army base in Alabama. This was an all CLT project, so it was the first one that Lend-Lease constructed purely from CLT. There was a significant interest in the blast resistance properties of CLT when this project was put in, because of course any structures on a military installation have to meet force protection requirements. But my interest in this project has been some of the metrics around the time and cost considerations of the construction. So moving into those time and cost benefits, what we find is that mass timber buildings typically feature time and cost savings that arise from a couple of areas. Those areas include the fact that the panels tend to be lighter with the same or even a higher strength to weight ratio than that of reinforced concrete. So the size of the crew that's used to erect these structures can often be reduced. So there's a labor savings. The size of the crane that's needed to put these panels into place, to hoist these panels, often can also be downsized. Additionally, the time to construct tends to be quicker because of the size and relative lightness of the panels. So there are indirect cost savings on the construction side as well, which involve the payment for items that exist on a recurring monthly basis. So temporary facilities, equipment rental, facility rental, overhead costs, things like that. There's some potential reduction in foundation size as well, due to the fact that you've got a lighter superstructure, and so there's less load for that foundation to support, and so smaller, lighter foundations are also possible. So again, if we look specifically at just two case studies, starting with Brock Commons in Vancouver, British Columbia, I'll focus your attention on the fact that the concrete podium portion of the structure and the timber installation began in May of 2016. And again, this is an 18-story building. The superstructure was complete by September of 2016. So an overall 4-month timeline to get that entire superstructure up. And this is not uncommon performance of what's seen with CLT. The question that often comes up is, how does CLT price out compared to reinforced concrete or steel? The material tends to be more expensive, but again, because of the time saving, you end up, this was a comparison prototype, you end up with a per square foot price that basically comes right in line. So in this case, Brock Commons came in directly on target with the same square footage price for a like concrete building. In the case of Candlewood Suites, just want to talk about some time reduction, because really time is where we're going to get into some of the carbon related issues. So on the time reduction side, you can see on the right-hand side of that chart that you had a smaller crew, your structural duration, so the erection of the actual superstructure of the building was reduced from 123 to 78 days. The number of person hours to complete the structure were greatly reduced. You had a higher structural production rate per day, and overall the project saved 3 months in the overall schedule. And so there's some interest and some questions about how changing the process could have a positive impact on the project's carbon budget. So we'll switch gears into that now, and I just want to look at a hypothetical $1 million worth of value in the U.S. commercial building industry. So we're just looking at all commercial buildings in the United States, and look at some of the life cycle emissions that go along with the building or with the completion of that much economic activity. So this is the Economic Input-Output Life Cycle Assessment Framework from Carnegie Mellon University. We find that for every $1 million of U.S. commercial building construction activity, we have about 414 metric tons of CO2 equivalent that are being released. And you can see the breakdown in the chart where the sources of those emissions are coming from. So the structure itself is responsible for, of course, the greatest proportion of that. And then we break down from there with electricity consumption and on. But where I really want to focus our attention is on the emissions that result from cement production and iron, steel, and ferroalloy products. So the cement that's going into the concrete to generate the reinforced concrete for these buildings, and what's going into the production of either structural steel or rebar for that reinforced concrete. Similarly, and I'll get to this point a little bit later in the presentation, I want to look at electricity and truck transport pieces of that emissions budget as well. And we'll take a look, and we need to be careful about scale as we go through some of these numbers, but we'll take a look at how electricity and truck transport impacts may be mitigated as well. So we'll start with conventional materials. And again, we're just going to take $1 million as kind of our hypothetical amount of activity. So again, this is $1 million worth of steel. We find that generating that $1 million worth of steel in the US produces about 1,400 metric tons of CO2 equivalent. If we go into ready mix concrete, we find that we're getting about 2,240 metric tons of CO2 equivalent through that amount of activity. And let's see if my pointer will work too, my cursor. With ready mix concrete, the vast majority, and you can see the numbers here, I mean, this is an order of magnitude difference, is coming from cement production. And you know, this is nothing new. We've known for years that cement production tends to be the place where we see the greatest use of energy and the greatest potential for greenhouse gas emissions from the concrete industry. And so we've taken steps within our industry to try to replace some of that cement with things like fly ash and other materials that reduce that overall burden. But this is still where what we're looking at per $1 million of ready-mix concrete manufacturing. So if we flip over now to some of the alternatives, you know, unfortunately, we don't yet track mass timber as its own industry segment, and this EIO-LCA model from Carnegie Mellon, if you're familiar with it, tracks along NAICS codes. So if there's no North American Industrial Classification System code, you have to find analogs. And so I used veneer plywood and engineered wood as my analog, and found that for $1 million of producing that material, we're at about 442 metric tons of CO2 equivalent. So this, you know, in terms of the scale of these numbers, the order of magnitude of these numbers, this supports some of what we've seen in terms of looking at the overall carbon budget for these buildings once they've been constructed. But now let's look at vehicle usage during the process as well, and we'll use Redstone Arsenal as an example. We know that we had 45 less days used for the structure. We had 8 fewer workers on site. And we can look at the tiered emission standards that have been brought into play in the US for vehicles. And basically, once you get above a 135 kilowatt engine, the tier 3 emission standards from 2006 capped all of those engines at 3.5 grams of carbon monoxide per kilowatt hour. So we can look at some of these reductions and say, okay, in a scenario where we're not sure exactly what has been emitted or not from one of these buildings, how can we do some calculation to tell us what the impact of less construction time, smaller crew, less crane utilization might be on the project's carbon budget? And what we find at the very, very minimal end is that we might be reducing about 1,000th of a metric ton of carbon monoxide from cranes. And that's before we think about downsizing cranes, because there are some cranes that have a small enough engine that get below that 135 kilowatt sizing. So you would actually be in a different emissions category in terms of those tier 3 standards. And then you see we reduce some carbon again from having fewer crew vehicles over that 3-month shorter duration for the project. So not large contributions when you again consider that $1 million worth of concrete is giving us over 2,000 metric tons of carbon equivalent. But, you know, again, a contribution to the project carbon budget nonetheless. The other issue, though, to consider is transportation, because one issue with doing mass timber construction in the United States right now is that we do not have a large network of, particularly of cross-laminated timber manufacturing facilities. So in the case of the Redstone Arsenal project in Alabama, they were sourcing CLT panels from Nordic Structures in Quebec and quite a ways into northern Quebec at that. So they had about a 1,500-mile trip to bring those panels. And so what I wanted to do was just look at how transportation of materials plays into, again, the carbon budget for those materials. We started with 1 cubic yard of site cast concrete. So ready mix concrete that you're going to bring to your site and cast on site. In the case of Redstone Arsenal, there's a ready mix plant 11 miles away from the location of the building. And that's fairly common in most locations in the United States. Most places are within a reasonable distance of a ready mix plant. Otherwise, you couldn't get the ready mix to your site before it started to cure. So you see for 1 cubic yard of site cast concrete, you can see the number. You don't even generate a bar on this scale for CO2 equivalent in terms of metric tons. And that 1 cubic yard of site cast concrete comes out to about 4,050 pounds. If we then take the equivalent amount of CLT, so 4,050 pounds of CLT, we find that driving that CLT from northern Quebec yields 0.4 of a metric ton of CO2 equivalent. But we now have a new plant going in, International Beams in Alabama. It's only about 300 miles away from that Redstone Arsenal site. So you can see what that vehicle emission reduction per unit, per that 4,050 pound unit would be. Now you can take those numbers, I don't have it in the slide, but you can multiply those numbers by about 3,300 to get to the equivalent amount of material that was used on the project. So if you want to get to the total budget for carbon coming from transportation of the materials themselves, just multiply these numbers by 3,300. I do want to take a couple of minutes real quickly to get into just talking about changing how we might look at mass timber, though, and where some of the carbon budget for CLT and other mass timber products may come from. So we're looking at the possibility of using salvaged lumber to manufacture the product. The takeaway on this slide is that in North America, we don't really do very much in terms of recycling and reusing lumber. Most of it ends up to the landfill or to incineration or downcycling. So where the carbon budget, would be perceived to be negative at that point. So that motivated us to do a study looking at salvaged reclaimed lumber coming out of old homes in Michigan and whether or not that could be put into production for CLT or glulam. I won't bore you with the details on these slides other than to tell you that on this slide, we found that 84% of our samples from one specific home that we tested passed the E3 stress class, which is the most common entry classification for lumber going into the manufacture of CLT. So 84% of our samples could pass going into the CLT manufacturing process. So then we said, okay, so what does that mean if we could take a house worth of lumber and turn it into CLT? What would that mean for carbon budgets? How would we now change our project carbon budget by accounting for carbon in other ways? And so what you see on the left-hand side of this slide is what happens when you landfill 8.6 tons of wood, which is about what we find in an average house in mid-Michigan, versus what would happen if you could put 5 tons of that 8.6 into source reduction. So use it to replace virgin material in the manufacture of CLT or glulam. If you still had some recycling and some potential landfilling and combustion for material that was not of a good enough quality to be reused structurally, per home, you would be saving about 6 metric tons of CO2 equivalent, which is about the emission, annual emission from one passenger vehicle. You can read the rest of the impacts. But just hold on to one passenger vehicle, since that's going to be the easiest one to remember on the next slide, because we don't just have one house that needs to be dealt with because it's abandoned in Michigan. We have 226,000 of them in Michigan. So now if we could start putting that material into productive use, you just start to get the sense of where the scale of this could go as we start thinking differently about how we source material and looking at this as part of the overall carbon budget and carbon management strategy, both in terms of virgin timber and salvage material that would otherwise just go to the landfill and produce a net release of carbon at that point. So when you look at this volume of lumber in Michigan, I just put it into perspective in terms of what those numbers mean. 903 million board feet. It's a lot of furniture. You can read the numbers. And the point is, we're probably not going to be able to salvage all of it, which is why most of it goes to the landfill and becomes carbon, becomes a source for atmospheric carbon. But you could take that material and manufacture 531 new Brock Commons buildings, which, again, I'm not saying that that's what we're going to do, but I just want to start to change some thinking and poke a little bit about how we might rethink how we handle some of this material. I'll close with a final slide on looking at use phase energy benefits in mass timber construction. We're doing a little bit of work now on a new project that's being developed where we basically took a hypothetical 1,000 square foot building module. This is going to be for a high-rise mass timber building located in the upper Midwest, but they're doing it in 1,000 square foot modules. So we took one module. Design options were either glulam with CLT and concrete floor and roof decks, or a steel frame with concrete, steel and concrete floor and roof decks. We modeled that module using eQuest with the DOE2, the DOE2 energy simulation engine, and you can see what we came up with. Basically, we believe on an annual basis, we would come to about 7% savings in our energy budget from that building. And given our location in the upper Midwest, the majority of those electricity BTUs are coming from coal-fired power plants. So again, we're looking at something where there's an additional carbon benefit to the budget for the project beyond just the material itself, thinking more broadly about where these benefits come from. And where we're going with this for the future, we are working on a time and cost development tool, which is funded by the Forest Service right now. And I only bring that up because if we have a better handle on the time piece, especially, then we can connect the time piece to development of a full LCA model for mass timber building prototypes. So right now, we really can't get to that point. We'd like to. And so the first step is getting that time tool developed fully, and then moving into an LCA model development for those building prototypes. And one piece that we're particularly interested in is the crane usage model and what those fugitive emissions and what the carbon budget then looks like when you start to change crane usage, both in terms of the hours that the crane is running, as well as the size of the crane that's required for the project that's being built. So with that, I thank you for your time, and I will turn this back over to Lauren. I look forward to your questions.
Okay, thank you very much. Let me see if I can successfully share my my PowerPoint this time, because apparently I did not. Uh-oh. Well, let me get you started on the first question that I have here before I fuss with that. So thank you very much. You both covered a really robust range of information. We have some great questions rolling in here. So I'd like to get you started. I think, Elaine, we have a few questions towards you first. So maybe I'll kind of start with some more of the landscape-oriented questions, and then we can end with some of the more like technical CLT questions, which you both may be able to answer. The first one is, Elaine, could you talk a little bit more about the increased productivity in forest landscapes? And according to your findings, is this something that we've reached the extent of, or is productivity still increasing?
I think that depends on the region and the intensity of management. So that example I showed with the 13 times increase, I don't know how much more they can go, but that's a pretty phenomenal increase from the 1940s. We did have some discussion, sort of internal discussion here with some silviculturalists about a year ago, and we're like, well, right now we're at least double what we were in the 1950s. And keep in mind, in the Pacific Northwest in the 1950s, they were harvesting old growth timber that was, 4 feet in diameter and 200 feet tall. And now they're harvesting stuff that's about 50 centimeters. So that's 1.5 feet, 2 feet in diameter. and quite a bit shorter. So the resource use efficiency, I think what we did find is that we're not getting as much volume, but we're getting more volume on more acres because your superlative sites are not as common as we would expect. At least a doubling. We think we can do better. And certainly with investment, I would expect that would come to pass. Other regions, for example, in the Northeast, they don't do a lot of intensive management there. So I think there's quite a bit of opportunity there to increase productivity. Some of these other regions in North America, in particular, there's some real challenges with increasing productivity, just because of the climate. The Southeast and the Pacific Northwest are two ideal climates for growing softwood, and well, the Southeast also hardwood lumber. So I hope that's helpful.
Yeah, I think that is helpful. Thank you very much. And one of the earlier questions, which you ended up sort of answering, but I think that this question came in before you addressed this, but there was some curiosity about what is the reason behind the large mortality that's happening now in the forests. And I know, again, you kind of explained this a little bit, but I thought I would still bring the question in.
Well, most of the national forest acreage in the U.S. is actually in the West, in the 11 Western states. And so that particular chart that looked at all of that mortality is in the 11 Western states. A lot of it is related to insect and disease outbreaks in the interior. We call it the Inland West. So that's your drier forests east of the Cascades. It's not your temperate rainforest where some of those other productive sites are. Insects and disease and wildfire. We've had a doubling of wildfire acres burned since 2000 relative to the time period prior to that. And we've had just some tremendous outbreaks of insects and disease, which are driven, somewhat by the age of the timber, how old those forests are, and somewhat by, there's certainly a climate signal in there. Whether it's a long-term signal or a short-term signal, we can't argue that it's a signal. And it's a pretty substantial signal that's really creating a tremendous stress in these forests.
Thank you so much. And another question specifically related to CLT and some of the graphics that we saw comparing different types of wood products and carbon storage. And this participant asked, why does CLT store so much more carbon than traditional lumber and plywood products?
Because if you're looking at it on a square meter of wall, there's so much more wood in that square meter of wall. So it's just purely a function of the volume of timber that's used to build a square meter of wall of CLT. If you look at that, I didn't put up a picture of CLT, but George did, where he showed that panel that's basically 7 2x4s thick, and it's all stacked together. There's no airspace. In a traditional lumber wall, you would have maybe 16 inches on center. You'd have 1 2x6, and so there's just a tremendous amount more wood. Therefore, it takes more wood to build the wall like that, and it stores more carbon because wood is about 50% carbon. Depending on species, it's like 48 to 52. So 50% is a good round figure for us here, at least in North America.
Thanks, and we are getting some really great questions here, so I can already tell we are going to run out of time. But I wanted to bring one to you, George. There's some interest in the idea of salvage timber, and somebody has asked, does it have to be a certain quality to be used? And wondering, does the structure that it ends up being used in, does that dictate the level of quality that could be used?
Yeah, it does. And that's one of the issues with reusing this material right now, is that building codes are either silent, or when they're not silent, they're actually restrictive towards the reuse of material that has sat under a structural load once before without that material getting recertified. And so it's typically been a cost barrier, because the flip side is you can go to Home Depot and buy a 2x4 for about 50 cents a lineal foot. So it's really difficult for dimensional lumber to absorb all of the preparatory costs that would have to go into reusing it in that form to get recertified. That's why we started looking at CLT and glulam, because higher value product, we believe it can absorb more of that preparation cost. But your question is spot on. Even to manufacture glulam or CLT, you still have to meet certain standards for that wood. So when we've tested the wood that we're bringing in from homes, we're testing it to the most common entry standard for virgin timber being put into the manufacture of CLT. The other opportunity that we believe is there is with glulam beams. If you, when the PowerPoint goes live, go back to the slide where I had the CLT picture on one side and the glulam picture on the other side. I had a cross-sectional diagram of the engineering layups for glulam beams, and I won't bore you with the engineering reasons for this, but basically the further to the center of a glulam beam that you get, the lower quality wood that can be put into that glulam. You basically don't have, you've got compressive and tension forces that cross and zero out in the middle of those beams. So as we start to think again about what the long-term implication of this work is, it might just be matching the quality and grade of the wood to the highest and best application for reuse, and then thinking about it that way. Because certainly not all wood is going to be able to be put into CLT production. Some may not be able to go into glulam production either, and then we need to think about what the next option is before going to the landfill and becoming a carbon source.
Thank you for that. And we usually end right on the hour, but I do want to ask one more question to get both of your responses. This one, and again, recognizing that we do have a good number of additional questions that we will follow up with the speakers on. So thank you so much for submitting them, and apologies that we can't get to them all in the session. But we had a really nice question here. What are some of the largest barriers to getting advanced wood products like LVLs or CLTs to replace traditional construction products like steel or concrete? And then they asked, is it important to convey potential market opportunities to landowners or environmental benefits? You know, what are your thoughts working in this space?
What we've seen directly from some attitude surveys is that, so the code issue was one, and now we think we're maybe working on that a little bit. But within the practice of building design and building construction, where we saw some of the barriers in the attitude survey that we've been working on, is generally just a lack of knowledge and lack of familiarity with the product. And there's a lot of, I don't want to say fake news, but I guess I should say fake news because it's kind of what it is about, you know, well, the material burns. It doesn't have good fire resistance properties. It doesn't have good seismic properties. It doesn't have good insect resistant properties. And so the construction industry tends to be very conservative. And so we shy away from those types of opportunities in the absence of more information. So better information, connecting scientific results to end users is going to be really important. I really think the carbon story and the environmental benefit story is huge to tell in this as well. I'll put it back to Elaine if you have anything you'd like to add.
Well, I think, I mean, there was a question about what do the landowners do? And I think the landowners, I mean, CLT isn't the first product. It's a stage in production. Before you produce CLT, you have to produce lumber. And so you need a lumber market, which is where the landowner would sell their logs to. They're not going to sell them to a CLT plant because they need them to come in as lumber. I would agree with George that there is some need to help people understand that we are and can be and behave sustainably here. I think there is some inherent concern that if this really took off, then we just log everything to the beach, and I think that that's just not true. But it's a concern, and it has to be explored and explained, which is why when we started looking at these questions of supply and demand, it became pretty apparent that perhaps the easiest explanation was to just explain how it works in terms of supply and demand. If you don't have a demand, your supply tends to get developed in regions where it can get developed, or you don't spend much effort to actually grow forests, so you get what you get. And so in fact, your carbon sequestration potential on the land is likely to go down. And it's a real challenge in some of these areas that don't currently have infrastructure or are struggling with massive losses of forest due to wildfire and insects and disease. Just do a call out to a region that's been particularly hard hit, and it's not in the US, it's in Canada and British Columbia. From about 95 to 2010 or something, they had 35 million acres of forest that was affected by mountain pine beetle. That was where they were producing their wood. They were able to salvage a huge amount of it, and then in the last couple of years, they've had 2 back-to-back fire years that have burned 6 million acres each year, practically, burned the remaining wood. So we can expect that they're going to lose their infrastructure because they don't have a supply, which means then how do you reforest all of that land that you didn't even harvest? It just was lost to these kind of mortality events. We see the same challenge in the interior West when with massive fires on national forest lands. There isn't any money to reforest it. So the two need to go hand in hand, and you have to have the supply to have the infrastructure. You have to have the infrastructure almost to get that supply to keep going. And that's why it's a sector. It's not an individual thing. It's a sector. We have to think about it as a sector to figure out how to make this work and be sustainable about it. I mean, George is right. Until we figure out that end and do a better job, we have to figure out that end and do a better job there. But we also have to figure out how do we ensure that that sector remains sustainable.
So thank you very much for that taking the time to answer the additional questions and those robust responses. We are over our time, and we do have some really great comments and questions. So we will be following up with you both separately, but I did want to take a moment to remind everyone that this is recorded. It will be posted to our website, and along with supplementary materials, including slides. And so that'll be available in just a few days. I'd like to thank our speakers, our guests, Elaine and George. Thank you very much for your time in preparing and giving your presentations today. And I'd also like to thank members of the Forest Climate Working Group and the Forest Climate Working Group Steering Committee for their support and guidance in developing this series. So again, thank you to everyone also that's joined. We appreciate your time, and please reach out to us if you have any questions. Everything will be on our website shortly. And thank you again to everyone. Have a great afternoon.